Hey there, it's Jason from Codemanship with another video diary entry. If you're enjoying these videos, please like and subscribe and ring the bell for notifications. So today I want to talk about the P word, polymorphism. And there's quite a lot you can say about polymorphism. It's very much a central plank of good modular programming, object-oriented programming and functional programming, for example. But I wanted to start by just mentioning that because I work with a lot of developers who are relatively new to programming, and one of the things I've noticed, particularly developers who've recently completed computer science degrees, is that they have a tendency to think procedurally. So they have a tendency to think in terms of branches and loops, for example, to solve their logic problems. And I've just got a little example of this. I've got this area calculator class here, and it needs to calculate the area of different kinds of shapes. And this is sort of typical, maybe a little extreme, but typical of the kind of thinking that I see from less experienced object-oriented programmers, where their first instinct is to declare some kind of enum for different shape types and then have a big switch statement. Problem with switch statements, of course, is they have a tendency to grow. We get more and more cases as we add more and more kinds of shape, for example. And they tend to get complicated, and they tend to make our software pretty rigid and brittle because we're constantly having to change them. Now, the whole point of polymorphism, really, in programming is to allow us to make decisions in a smarter way, in a more modular way. So the equivalent of this area method on our area calculator, a polymorphic version of that would be maybe, for example, to declare an interface for a shape that has a way of getting the shape's name and the area of the shape. There's our function defined there. And maybe we would implement that for a circle, and we would implement that for a square, and we could do a rectangle and a triangle, as many others as we want. And as long as they all implement the shape interface, then that means that we can add new kinds of shapes or change the way that shape areas are calculated without having to rewrite any client code. So it basically allows us to change our system, which is really the whole point of modular programming. Allows us to change our software or our system by swapping out a module rather than having to rip up a whole bunch of existing modules. I've got a little main method here that I can run. You can probably see the output of it at the bottom there. Let's just run it again, make sure it's working. And it's got a print area function you'll see there. And that just accepts, that's the polymorphic part of it. That's working, lovely. That's the polymorphic part of it. It only knows about the shape interface. So any class that implements shape, we should be able to pass that into this function and get an output of the area for that particular kind of shape. That's essentially what polymorphism is all about. Okay, now, a lot of developers, as I said, have a tendency not to think in this kind of way. They don't think about, well, we could have different kinds of types of shape. They tend to think, well, we could have a big switch statement if there are different types of shape, rather than using polymorphism in this kind of way. Polymorphism is a mechanism for making decisions in our code where the client decides, oh, I want you to print the area of a square. No, I want you to print the area of a circle. So we're replacing that enum, that nasty enum that we were passing in there in the big switch statement. We're replacing that with polymorphism. And that's actually the name of a refactoring. Replace conditional with polymorphism. The other thing I think that confuses a lot of developers is they don't actually know what polymorphism is, or rather they don't know how it works. And this is particularly true of developers who are not doing object-oriented programming, who think that polymorphism is a concept that only applies to objects. Now, if you've worked in C, which is, I think, 50 years old next year, it's quite an old language now, you may, if you're an old lag like me, you may have attempted to do some object-oriented programming in C. C is not an object-oriented language. It does not have the concept of classes. But in actual fact, you can do a kind of object-oriented programming, and you can achieve a kind of polymorphism using function pointers. So I just wanted to demonstrate. I've got a C version of this project here, where we've got our shape defined here. You'll see that in a minute. Let's take a look at our main method. So we've got the same kind of setup here. We want to print the area of a square. We want to print the area of a circle. The data is the same. And we've got our print function, and that is accepting this thing called a shape. And you'll see the shape is a user-defined type. It's a struct that has slots, fields basically, where we can hold function pointers. A pointer to an area function or the implementation of an area function, and a pointer to the implementation of a getName function. And it's the function pointers that are the magic basically here. Once we have the ability to essentially treat functions as data, to have pointers to functions, for example, that we can resolve at runtime and even swap them around, so we can put pointers to different function implementations in the same slot, then it becomes possible to achieve polymorphism through this mechanism called dynamic dispatch. Now, dynamic dispatch, let's take a quick look at the Wikipedia entry. In computer science, dynamic dispatch is the process of selecting which implementation of a polymorphic, there's the P word, a polymorphic operation, a method, or a function, it's not just an object-oriented thing, to call at runtime. It is commonly employed in and considered a prime characteristic of object-oriented programming, but as you'll probably realize, you can also do it in functional programming. What did you think those lambdas you were passing into those functions were? They are pointers to function implementations. Okay, so that's dynamic dispatch. And what we're doing is, in this code, is we are constructing a user-defined type. Let's go and take another look at it. So we have a type definition for a shape, which reveals very little. And then we have a definition of that struct down here. It has a thing called an object. I'm just going to rename that actually to make it a bit more obvious. I'm going to call that self. Let's see if that works. And the job of the object is to hold the data of the thing that these functions are going to be working on, the shapes that these functions will be working on. So it holds the data. And then we've got, and this is the magic part, we've got these slots here essentially defined for function pointers with certain signatures. The area function there, which returns a float, and it accepts an object. Remember, it has to act on the data, so it accepts a pointer to the data that it's going to be working on. And similarly here, we've got a function that returns a string called getName, and that too accepts the object as the parameter in, the first parameter. And that's really, when we talk about object-oriented programming, when we say the object, that's what we mean. In most programming languages, it's an implicit or hidden first parameter to every method, essentially called something like self or this or me in Visual Basic and things like that. But do this to this data, do this to this object. Okay, so that's how it's defined in terms of its interface. This here essentially defines an interface, and we could include the data as well if we wanted to. But this is, an interface is just a collection of function pointers. That's all it is. For example, in C++, back in the good old days, and in many other languages as well, we had this idea of a virtual method table or vtable or VMT, which is essentially a table of function pointers. We're just storing the functions like they're fields. You can do this in JavaScript, for example, with JavaScript objects. You can assign references to functions, to fields of objects, and give them names and stuff. So this is a slot for a reference to a function implementation that has this signature, and we've called it area, and here's one called getName. So we're defining the signature of the functions that can be assigned at runtime. Now in our implementations, let's take a look at our implementation of the square, for example. You'll see we've got implementations of the area and getName functions. So they have different names, they have to in C, so that we don't get a naming conflict. But very importantly, they have identical signatures. So a square area returns a float and accepts an object. And here's where it might start to look a little more object-oriented to you. So we're passing in the reference to the object, and we've called it self. And then we're referencing self. So we're talking about the length of that shape, for example, the length of that square, or the name of that square, and so on and so forth. And we'll see we've defined the actual structure of the object, the structure of the data that we're working on inside this file that is not exposed in a header file. So only code in this file can actually see it. So it's encapsulating the data, it's hiding the data, so that nobody else needs to know, and nobody else can work on it, no one else can change it. Okay, and then we have what is essentially a constructor. It's defined in the header file and then implemented down here in our C file, where we create the object, we assign data to it, the name and the length, which is from that constructor parameter for a new square. And then we define our shape, our square, attach the data to it, and then attach pointers to the functions, the implementation functions, to those slots, to those fields in that user-defined type. So that the square that gets returned has the square area function assigned to the area field, and the square name of a function assigned to the get name field. So that when we call area, we're calling this function with an object that has a length, and we multiply, basically we square the length for the area of the square. Fairly straightforward. And we do a similar thing with the circle. So we define the data structure of the circle as a name and a radius. And then we define the functions for calculating the area and returning the name of the shape. And then again, we have a constructor for a circle that takes a radius and builds the data, assigns the data to the shape, and then assigns pointers to those function implementations to our area and get name fields for the function. So that in our main method, we can call the area function on the shape. And this is where dynamic dispatch comes in. It's just a pointer to a function. So it's resolved at runtime as to which actual function implementation it's pointing to. And you'll see there we're passing, so this is the slightly clunky part. We have to pass in a reference to the data. Now, if you wanted these functions to invoke each other, so for example, you wanted helper functions, you would have to pass in the whole object, including all those function pointers. But here it's just using the data. So I'm just passing in a reference to the data. And the same thing here. Now, all that object-oriented programming really does is flip that around. Flip that around. So when you say, for example, shape.area in Java, what you're actually saying is, give me the area of this shape. So if we go back to our Java, give me the area of this shape. Let's go into our circle, for example. There it is. There's this pointer. It's an implicit thing, an implicit parameter, if you like, of every constructor, of every one of these methods. We can make it a bit more explicit. This dot name is similar in a way to self. It's a reference to an object, and it identifies which object. And in the case of Java, including all of the function pointers, including its table of function pointers, that we're actually referring to. Which instance are we referring to? In other words, if you go back to our C, in other words, this is an instance. This is the instance that we're talking about. It's just that we're passing the instance into the function rather than using the instance before. But I suppose that there probably looks a bit more familiar. Shape.area or shape area makes more sense to object-oriented programmers. But it is polymorphic. We have different implementations of area, different implementations of getName. They're being resolved at runtime so that new square and new circle are returning different types of shape, basically, that do those things in different ways. And when we print them, we're getting different behavior, polymorphism. So that's all polymorphism is. It just depends on this thing called dynamic dispatch, which works essentially with function pointers or function references, where we construct data structures or tables, however you're doing it, of those function pointers so that we can essentially attach them to an object. For example, how they're attached to the instance of the shape. In fact, maybe even better. Let's go back to our... I'm overthinking this now probably, but let's do it anyway. Let's just call this instance. Like that. Just to make it absolutely clear that that's the shape, that's the particular shape that we're talking about. And if we wanted, as I said, if we wanted these methods to call each other on the same object, then we'd have to pass the whole shape in, or figure out some other way of doing it. But it's totally doable. Again, a little more clunky, but it's totally doable. So polymorphism, the P word, it's really no big mystery. It's all based on function pointers. If you can treat functions as data or references to functions as data and pass them around and resolve them at runtime, then you have dynamic dispatch, which means you have polymorphism. And it's a way, essentially, of making decisions in a much more extensible way, basically through modular programming, rather than through horrible procedural programming like our nasty, our nasty switch statement there. So the switch statements can go. Anyway, that's me for today. Hope you're doing well. Until the next diary entry, take care.